Welcome to Switchgear, Protection and Relay Coordination, a comprehensive guide. In this training, we will analyze the hardware and logic required to isolate faults and protect grid infrastructure. In this comprehensive training on grid infrastructure protection, we will transition from physical hardware to mathematical logic. First, we examine hardware interrupters, analyzing circuit breaker evolution and SF6 gas properties. Next, we dive into the mathematical brain, relay coordination, breaking down the IDMT formula and distance relay MHO characteristics. Then we cover unit protection, specifically differential logic for critical assets like transformers and bus bars. Finally, we anchor our system with safety, reviewing earthing and grounding design per IEEE Standard 80. To understand modern grid protection, we must first look at the foundational technologies of fault isolation, oil and air blast circuit breakers. In early power systems, bulk oil circuit breakers were the standard. When contacts separate during a fault, an intense electric arc forms. The surrounding oil serves a dual purpose. It acts as a robust insulator, while the arc's heat vaporizes the oil into hydrogen gas, cooling and quenching the arc. But as grid voltages increased, the flammability of oil became a serious limitation, driving the transition to air blast technology. Air blast breakers use highly compressed air to violently blow out the arc, enabling much faster fault clearing at higher transmission voltages. As we move beyond legacy oil and air blast technologies, we encounter the vacuum circuit breaker, or VCB. VCBs are the industry standard for medium voltage applications, typically ranging from 11 kilovolts to 33 kilovolts. Inside the sealed vacuum bottle, when a fault occurs, the contacts separate. The immense heat vaporizes the contact material, creating a highly conductive metal vapor arc. However, the true advantage of a vacuum is its rapid dielectric recovery. The moment the alternating current crosses zero, this metal vapor condenses almost instantly. The vacuum regains its insulating strength, permanently quenching the arc. This mechanism ensures a remarkably long life cycle and requires minimal maintenance. Moving beyond vacuum interrupters, high voltage applications heavily rely on sulfur hexafluoride, or SF6 gas. SF6 is a dense synthetic gas that revolutionized power system protection. At a molecular level, SF6 is highly electronegative. It has a strong affinity for capturing free electrons. When an electric arc occurs, SF6 rapidly absorbs the conducting electrons, extinguishing the arc. To achieve optimal performance in switchgear, SF6 must be pressurized. At an operational pressure of 3 bars, it exhibits an extraordinary dielectric strength of 25 kilovolts per millimeter. To put this into perspective, its insulating capability is vastly superior to that of standard air, allowing for highly compact equipment design. This exceptional dielectric superiority makes SF6 buffer breakers the standard for extra high voltage grids. While SF6 is an exceptional dielectric, it comes with a severe environmental cost due to its extremely high global warming potential, or GWP. Because of this climate impact, the power industry is actively transitioning towards eco-friendly, SF6-free alternatives for modern switchgear. These solutions utilize clean gas alternatives such as clean air or specialized synthetic mixtures like Novec, which offer a near zero global warming potential. However, replacing SF6 requires engineering trade-offs because these clean gas alternatives have slightly different dielectric properties. The resultant switchgear often requires a slightly larger physical footprint. Despite the larger size, this shift is a critical step in developing sustainable grid infrastructure. We have explored the hardware that interrupts fault currents, but how does the circuit breaker know exactly when to open? This is the job of the protective relay, the brain of the grid. It continuously monitors the system using current and voltage transformers. Upon detecting an anomaly, the relay applies its logic. If a fault is confirmed, it instantly sends a command to the breaker's trip coil. This sequence, sensing, deciding, and acting, is driven by selectivity, ensuring we only isolate the faulted section while the rest of the grid remains active. To understand how relays coordinate, we must look at the mathematical heart of overcurrent protection, the IDMT formula. IDMT stands for inverse definite minimum time. The standard IEC formula calculates the relay's operating time, T, using several key variables. In the numerator, we have TMS, or time multiplier setting. This directly scales the operating time, allowing engineers to shift the curve. In the denominator, the ratio of actual fault current I to the peak setting current I's is known as the plug setting multiplier, or PSM. The constants k and alpha define the specific shape and steepness of the curve. Notice the mathematical relationship. Because the plug setting multiplier is in the denominator, as the fault current increases, the denominator grows exponentially. Consequently, the operating time decreases. This inverse nature ensures that more severe faults are cleared much faster, preventing catastrophic thermal damage. The alpha parameter in the IDMT formula defines the relay's characteristic curve. Let's plot these on a log-log scale of operating time versus fault current. First is the standard inverse, or SI curve. It offers a moderate time reduction, serving as the baseline for general distribution. Next, the very inverse, or 6 curve. Its steeper slope reacts faster to high fault currents. Then we have the extremely inverse, or EI curve, dropping off sharply. It is specifically chosen for coordinating with fuses or riding through transformer inrush currents. Finally, the time multiplier setting, or TMS, shifts these curves vertically. Adjusting the TMS scales operating time proportionally, enabling precise time grading between relays. Long transmission lines require advanced distance protection. Instead of just measuring current, a distance relay continuously calculates the line's impedance using the fundamental formula Z equals V divided by I. To visualize this, engineers use the RX plane, a coordinate system where the x-axis is resistance and the y-axis is reactance. The line's normal impedance forms a vector here. The most common operating characteristic is the mu circle. Plotted on the RX diagram, it is a circle with its circumference passing exactly through the origin. When a fault occurs, voltage drops and current spikes, causing the measured impedance to fall dramatically. If this new point lands inside the mouse circle, the relay issues a trip command. Because the circle occupies the first quadrant, it is inherently directional, naturally ignoring faults behind the relay. To apply distance protection to a transmission network, we use a strategy called step distance zoning. Let's look at a transmission line connecting station A to station B. Our primary protection, Zone 1, is deliberately set to cover exactly 80% of the line length. Why not 100%? This restriction is critical to prevent overreach because instrument transformers have inherent measurement errors. A full 100% setting could cause an unwanted trip for external faults. Therefore, Zone 1 operates instantaneously with zero intentional time delay. To protect the remaining 20%, we configure Zone 2. It extends into the adjacent busbar but operates with a deliberate time delay of 300 to 500 milliseconds to ensure selectivity. We now move to a highly selective strategy known as unit protection, achieved through differential relay logic, or NC code 87. Differential protection relies on Kirchhoff's current law, continuously comparing the current entering a protected zone with the current leaving it under normal conditions, or during an external fault. The entering current matches the leaving current, meaning E in equals I out. However, if a fault occurs inside the protected zone, this balance is disrupted. The relay calculates the differential current, ID, as I1 minus I2. If ID is non-zero, it instantly commands the circuit breakers to trip, ensuring only the faulted asset is isolated. Applying differential protection to transformers introduces unique challenges that aren't present in simple busbars or transmission lines. First, consider a typical delta star transformer. The primary and secondary voltages differ, meaning the nominal currents differ. This requires careful turns ratio compensation. Second, the delta star connection creates a 30-degree phase shift between the primary and secondary currents. To correct this, we use vector group compensation. Traditionally, this was solved by wiring the primary CTs in star and the secondary CTs in delta, effectively reversing the phase shift before the relay. Finally, energizing a transformer draws a massive magnetizing inrush current. Relays use harmonic restraint, detecting the second harmonic to block false tripping. Beyond transformers, differential protection is critical for two of the most valuable assets in a power system: generators and busbars. For generators, stator winding faults can cause catastrophic mechanical and thermal damage. A dedicated differential zone tightly envelops the stator, comparing neutral and terminal currents to instantly detect internal shorts. Meanwhile, the bus bar is the central nervous system of the substation, where multiple incoming and outgoing feeders converge. A bus bar fault is the most severe event in a grid, potentially causing total substation failure and widespread blackouts. Therefore, bus bar differential protection must be exceptionally fast and secure, often utilizing high impedance schemes to prevent false tripping. While relays and breakers protect the physical infrastructure from thermal and mechanical damage, we must also address the most critical asset in any substation: human life. This brings us to IEEE Standard 80, the globally recognized benchmark for AC substation grounding design. The primary objective of this standard is to establish safe limits for potential differences under fault conditions, ensuring that personnel are not exposed to lethal electric shocks. To achieve this, engineers design what is known as a ground grid, a buried mesh of interconnected bare conductors. This grid safely dissipates massive fault currents deep into the earth, stabilizing the surface voltage. When a severe electrical fault occurs in a substation, massive fault currents are injected into the earth through the grounding grid. Because soil has natural electrical resistance, this current creates a voltage gradient, radiating outward like ripples in a pond. These concentric rings represent equipotential lines, illustrating how the voltage drops rapidly as you move away from the fault point. This steep gradient introduces two critical life safety hazards defined by IEEE Standard 80: touch potential and step potential. Touch potential is the dangerous voltage difference between a person's hand touching a faulted structure and their feet on the surface. Step potential is the voltage difference between a person's 2 feet spread apart on the ground, bridging two different equipotential rings. Mitigating these lethal potentials is the primary engineering goal of any substation ground grid design. To mitigate dangerous step and touch potentials, substations employ a comprehensive ground grid. This grid is a network of bare copper conductors buried in the soil, forming a mesh across the substation footprint. During a fault, it distributes current into the earth. By reducing the mesh spacing, we effectively flatten the surface voltage profile. This flattened profile minimizes ground potential rise, or GPR, drastically lowering voltage differences between any 2 points. Additionally, a surface layer of crushed rock is applied, which has a naturally high electrical resistivity. This insulating rock layer increases contact resistance at the feet, further protecting personnel from fatal fault currents. We have completed our comprehensive journey through power system protection, analyzing the hardware and logic required to isolate faults. We started at the physical layer, examining how legacy interrupters evolved into high-performance SF6 and eco-friendly gas alternatives. From hardware, we transitioned to the mathematical brain of the grid: protection relays. We explored the IDMT overcurrent formula and visualized the MHO distance characteristic for precise transmission line zoning. We also applied differential protection to safeguard critical transformers, generators, and bus bars. Finally, we grounded our system in safety, applying IEEE Standard 80 to mitigate dangerous step and touch potentials. Together, these layers ensure a resilient and secure electrical infrastructure. Thank you for completing this training on switchgear and relay coordination. Please proceed to the assessment module to verify your knowledge.